Dear students, today we are going to take up one group Cc disconnections. Now the one group Cc disconnections are the ones which are seen most of the time. Why? Because we are discussing organic chemistry. So carbon-carbon bonds are the norm. And when two carbons, they will be disconnecting from each other. Obviously, one will be getting the positive charge and the other the negative charge. The positively charged or the negatively charged, if it is a positive charge, that means, in other words, it is electrophilic, electron loving. We have synthetic equivalents for such synthons as well, like Rx, that is RBr, etc. And if carbon has a negative charge, in other words, it is R negative, the synthon. For that too, we have got synthetic equivalents like RMgBr, where R is negative. So let us see as to how these disconnections can take place. Remember one thing, we are disconnecting with respect to one group. That is, we are taking into account the presence of only one functional group attached to carbon. The bifunctional ones we have done, 1, 3, etc. we have done because these we taken up in class for those of you who missed it. So again, we are just going over it. Now, this is R dash R double dash R. The carbon is attached to OH. So this is the functional. One group Cc. Now, this carbon will disconnect. It can disconnect either from here or from here or from here. It is one and the same thing. But when it disconnects, the R will be getting a negative charge. And this C will be getting a positive charge. The disconnection will be done in such a way because we know that we have not only the synthetic equivalents corresponding for the same, at the same time, we are also familiar with the chemistry or the synthesis backwards, or the actual synthesis can take place only when these are positioned like this. So R negative, the synthon disconnection, so one will be negative, carbon will be positive. The synthetic equivalent for the synthon is the Grignard reagent, where R is negative. And when this carbon now, when it is positive, we know electron deficient. So it will share an electron from oxygen, which has lone pair. As a consequence, oxygen will get the positive charge. A positive charge on an electronegative atom is not stable. So how can it remove this positive charge? It can be removed when H takes away this positive charge, is removed as H positive, leaving its electron pair behind. In other words, the synthetic equivalent for such a synthon is a carbonyl compound. So this is what type of a disconnection? 1, 1. Why are we calling it 1, 1? Because we are disconnecting the carbon which is attached directly to this functional group. So this is the one carbon, and it is being detached or disconnected at this point only. Can you see here? It could be here also. Even then, it is this point which is connected to the functional group. Hence the name 1, 1. Now let's move on to this disconnection, the other disconnection. As can be seen in this disconnection, this is the functional group. Now, with respect to the functional group, this is 1. So this time we are not doing 1, 1. That is, we are not disconnecting this. It could have been this disconnection here too. Then too we would have got our CHO or carbonyl. This time we are trying another type of synthesis, disconnecting it to the second. So this is, had we disconnected here the carbon which is attached to this OH, it would have been in this functional group, that would have been a 1, 1 disconnection. But we are disconnecting two places, two carbons away, not that carbon. This is one carbon, this is two carbon, and then we are disconnecting. So this type of a disconnection is a 1, 2 disconnection. Naturally, this disconnection will again lead to an R negative, and this will get a positive. Now, why this is the positive? This positive can take electrons from here. In other words, we are talking about an epoxide ring, a good reagent, very reactive reagent. When this takes up the electrons from here, obviously oxygen gets a positive charge. So H is eliminated and it leads to the formation of an epoxide ring. So one is the Grignard reagent. Again, in what type of a disconnection? 1, 2. 2 carbons away from the functional group. It is not on that carbon to which the functional group is attached. So this is now 1,2-Cc disconnection. Now this 1,2-Cc disconnection can also occur in such a way so that when we are disconnecting, now this is a carbonyl this time, when we are disconnecting, this is the functional group. So 1, 2. Again 2 carbons away. So R negative and R positive. Now negative would give us what? The Grignard. A positive here, let us see, will it give us some sort of a synthetic equivalent? We think of our chemistry if any such reaction takes place, but we very well know it does not, because otherwise it will lead to the formation, if we take a Grignard reagent, lead to the formation of an alcohol rather than this type of a carbonyl. So what is to be done is that we reverse it. In other words, we place a negative here and a positive here. And we now know that a negative here implies the alpha carbon. And the alpha carbon can easily form a carbanion because it is acidic. The hydrogens are acidic, so it will eliminate an H positive because this electron pair will be pulled here. As a result, in the presence of a base, this carbon will become positive, so this will pull electrons from here. This in turn will pull to the attached electrons, hydrogen. So the carbon hydrogen bond will become weak. In the presence of a base, we will get a carbanion. In other words, we are talking about an enolate. What are we talking about? An enolate, because this will be carbon negative, CO, and this CO consequently moving here, this double bond moving here, so this will be an enolate. And these type of reactions we have done in Michael addition as well as we have done it in our regioselectivity. So R now will be positive, so R positive will be RBr. Here now this negative. Now, how can this negative, if you remember or recollect a little about active methylene compounds, that in order to facilitate the removal of H positive from here, which is acidic, if we introduce another such electron withdrawing group, so this will become an active methylene group. And later on, by hydrolysis, ketonic or acidic hydrolysis, this can be removed depending upon what we require or what we desire. So hydrolysis will remove this entire CO2 and C2H5OH eliminated on hydrolysis, and we will get our target molecule back. So this too will create carbon negative, now this time more efficiently as we have got this. So this, in other words, generation of this type of a compound from the enolate. Now let's see the third type. So this was again 1, 2, remember, again 1, 2, because we are disconnecting 2 atoms away, 2 carbons away from the functional group. Now the case can be also that we disconnect 3 carbons away from the functional group. That is a 1, 3. So this is the functional group. So 1, this is first carbon, second carbon, third. 3 carbon away will generate exactly what I was mentioning earlier, that is an enolate 1, 2, and this will lead to, if you recollect, this is R negative, so positive alpha beta unsaturated. And alpha beta unsaturated is the one which will lead to our Michael addition. So this 2 is negative, this 2 is negative, but remember this is active methylene. So we recollect whenever carbon is negative like this, we recollect our Michael addition, see if the conditions are suitable. We recollect our active methylene compounds, see if the condition is suitable, and accordingly choose our disconnection. So here When this becomes positive, positive charge can be eliminated. How? If H positive leaves. So H positive leaves, leaving its electron pair, and because this bond has been dissociated, so a positive charge. This positive charge fulfilled by H positive leaving from here, taking the positive charge, leaving the electron pair. So we get an alpha beta unsaturated carbonyl compound, the perfect site for a Michael type of addition. So remember, enolate type and this here, because carbonyl suggests both types, Michael as well as enolate. In other words, Michael as well as these active methylene. So these are one group Cc disconnections, 1, 1, 1, 2 and 1, 3. So let's take a few examples. Now the first example here is that of the synthesis of alcohols. So we are disconnecting the Cc bond next to the oxygen of alcohol, the functional group. So this is the carbon and this is being disconnected. So 1, 1. What do we get? As we saw earlier in the summary in the initial sheet, that one will be negative, the other positive. The positive will generate a, because this carbonyl group, why? Because we know this is positive here. So this positive, the valency is fulfilled by the electron deficiency is fulfilled. How? By the lone pair of electrons on oxygen. So oxygen gets a positive charge, which by eliminating H positive and the electron pair, the bonded pair coming here now, forming a double bond. That is our carbonyl. So this is now CH3, CH3, CO. H has left because this was positive. Now this other negative automatically will form the Grignard reagent. And we very well know when a Grignard reagent reacts with a carbonyl, it leads to the formation of an alcohol. So this was the retrosynthesis. Now this is the synthesis. Grignard reagent formation, how? Taking this same alkyl halide, I've written directly over here now the synthetic equivalence, because we know what synthon will be formed here. This will be negative, so MgPr. This will be positive, so a carbonyl. And now this will lead to formation of this type of a compound. So in other words, we have finally got our target molecule, that is our alcohol. Now let's see the next synthesis. The next one is again a 1,1-Cc disconnection, similar to this, because we are disconnecting where we are disconnecting at this carbon 1,1, the same carbon which has this functional group. So it's a 1,1 disconnection. The same carbon containing the functional group. So this will get a positive charge, this negative, this will be the Grignard reagent, this will be the carbonyl. So again, one is synthesizing the target molecule. When one looks at the synthesis, this is the synthesis of our target molecule, that is our alcohol by the 1,1-Cc disconnection. Now let's take up this third disconnection, again a Cc disconnection, 1,1. So this is a more complicated molecule, and as we can see in this, that there is an ester group. And if you recollect your Rx disconnection, so the first disconnection is we will remove this entire group. The big group is removed, the ester. While going back, we know we can synthesize, therefore, this ester group. And so we can therefore disconnect it this way. So now what will we get? We will be getting this alcohol, because on ester disconnection. So an alcohol, and the other part of course can be an acid or an acid halide on this. And now once this has been simplified, that is our bulky group, the ester group disconnection has been done, CORX disconnection, which we did prior to this. So as a revision class rather, because we've done all this in class earlier. Now, and for those who did not attend this class, and a few others who wanted to know about it. Now see, we've got this and we've got this. Now what is this implying? What does this show, in other words? This is showing what type of a disconnection. Again, OH here, pH here. So if we disconnect it, we will get what? Because this is the carbon to which this functional group is attached. So what type of a disconnection? 1,1. Again, 1,1 Cc. This is phenyl ring, carbon and carbon. And we very well know this will give us a carbonyl compound and a Grignard reagent. This is pH negative, so a Grignard reagent. This is how it will disconnect. Now, the next disconnection after this is the one which we have done earlier prior to this, which will be, we can see, now we have to disconnect this group to simplify it. We are trying to simplify. See, we are thinking of the synthesis backwards. So, we are trying to know as to what is the reagent we are going to use to start our synthesis so as to produce this target molecule. So can we simplify it further? Yes, if we disconnect this, what disconnection will it be? Rx. And what type of Rx? So we see that with respect to this carbonyl, this will be a 1, 2, 3. 1, 3 Rx disconnection. And we know a 1, 3 Rx disconnection means that this will be positively charged. This is naturally a heteroatom, so it will be negatively charged. This positive charge can be eliminated in the form of H positive, creating a double bond here. So we get our alpha beta unsaturated carbonyl compound. And this is the simplest. So now we can start our synthesis starting from alpha beta unsaturated compound. So this alpha beta unsaturated compound in the presence of a base will obviously give us this connection. And now once this has been formed, what can one do in the second step? Because the last disconnection is the first in connection. The last step in retrosynthesis is the first step in synthesis, because now we are going for the actual thing. This was the reverse of synthesis. Now this is synthesis itself. So now this will lead to the formation of this bond between this and this alpha beta unsaturated carbonyl, because this will be CO, this shift of electrons, electromeric. As a result of this, double bond will shift here, and this will be getting a positive charge. This positive charge will be attacked by the nitrogen negative, or the nitrogen lone pair, we can say. And so a bond is formed and we get this product. Now in the second step, we know, because this is carbonyl turning it into an alcohol, reaction of Grignard reagent with carbonyls is the synthesis. So this is the Grignard, or this time now, see, this time we have, here we have selected organolithium, because organolithiums, they were selected, they always give a 1, 2, because there was this bond also. So though this has been satisfied by this group, but some of this must be present in the reagent itself, left over, so that it doesn't connect or synthesize a 1, 4, because we need a 1, 2. Direct addition to a carbonyl is a 1, 2. So OH and 1, 2 and pH here. So this leads to this and this alcohol. And now in the final step, the first step in retrosynthesis is the last step in synthesis. And so this is finally the esterification and formation of our target molecule. And this was all in the case of what type of a disconnection. Here we see so many things. We saw the esterification reaction. We saw to 1,1 Cc disconnection. At the same time also 1,3 CX disconnection. Now, can we synthesize aldehydes and ketones? Or till now we were doing the disconnection 1,1 with trying to synthesize our alcohols. Yes, we can, even our aldehydes and ketones. Now, how in this respect? Here, first one can go for a functional group interconversion. So, if this is the target molecule, functional group interconversion implies that any group which will convert to the carbonyl. Yes, we very well know. A secondary alcohol will convert on reaction back on oxidation to a carbonyl. So, this is the reaction backwards. And now, when we write here, we will be writing the one which will be carried when we are doing the synthesis forward. So synthesis forward means that we will be doing oxidation. So this is written for the functional group interconversion. So that on coming back, we oxidize, we get this ketone, secondary alcohol giving rise to a ketone. Now this is the functional group. We know for the OH disconnection here will give us one type of this will be a carbonyl. In this case, this is OH here, and an H over here. The fourth valency is satisfied by H. So a positive charge here, elimination of H positive will give rise to CHO. This cyclic compound, six membered with attached CHO. That is our aldehyde. And this obviously will form the Grignard reagent. So this forms the Grignard reagent. Now, can this be further disconnected or simplified? Let's see. Yes, it seems it can. How? Because this is now CHO. Can we simplify it further? Again an FGI, because alcohol will give us an aldehyde. Primary alcohol on oxidation gives an aldehyde. So if it can be disconnected further, we write here after a functional group interconversion alcohol, primary alcohol. And now again a 1,1-cc disconnection. A 1,1-cc disconnection leading to this cyclohexane ring negative and this carbon positive. 1,1 because this carbon has this OH attached to it. So 1,1-cc disconnection. And obviously what will be formed? A Grignard reagent. And here by elimination of H positive, we will get a CH2O, or we can call it HCHO, formaldehyde. So we have got the simplest of our synthetic equivalents, which will be our starting reagents. So let's see the synthesis. The synthesis again will start. How? Formation of the Grignard reagent. You could have written over here MgBr itself, no problems. So here we've written the cyclohexyl bromide with magnesium diethyl ether. It will give rise to our Grignard reagent. And this will react with, this will form with our HCHO. This will react and we will get this type of a product, which can be further made to react with our Grignard reagent, and this on further reaction will give us this alcohol. Here too an alcohol will be formed initially, and which is then oxidized to this aldehyde because it will be a primary alcohol which will be formed. So now this again on reaction will give us this secondary alcohol oxidation. We get this ketone, our target molecule. Now this is the synthesis of carboxylic acid, again by using this type of a disconnection. So we've taken various examples. As you can see, it is COBr. Now COBr, that is the acid derivative, we know will disconnect at the RX disconnection, so which will give rise to the Br negative and CO positive, and the CO positive with an OH negative gives this acid. So now this acid can again be formed. We are just thinking about it. How can it be formed? Can it be formed in some way? Yes, we know from Grignard reagent with carbon dioxide. So let's try that part. So CC disconnection, CC, and we've written Br here because from this we will be slowly synthesizing our compound. Now, how can this bromide be formed? This is CC disconnection. COH is removed because COH can't be added directly, so it is removed from here. This is, we are trying CC. Otherwise, we could have by oxidation of CH3 because toluene or oxidation drastic, but and because this is a methyl also over here. So this disconnection will lead to, we have written Br. See how why we've written Br. This on disconnection further, CC disconnection. So this Br we finally disconnected and written an amine. Now why an amine? Because we know that amines on diazotization will give us lead to the bromide diazotization. That is, if this is reacted with NaNO2 HCl 0 degrees centigrade and with copper bromide, so we will get this product. Therefore the use of our diazonium chloride. So this is our final product. So how do we start from this? Let's see the synthesis. As I mentioned, with this NH2 converted to Br, the simple Sandmeyer reaction, and then with this is NaNO2HCl giving us this nitrous acid and copper bromide and HBr. So this bromide will give us the Grignard reagent with magnesium, and we very well know this when this will be formed C6H5MgBr substituted at the fourth position with methyl group. This on reaction with carbon dioxide we know will give us the acid, because these halides when they are made to react with carbon dioxide, they lead to the formation of the carboxylic acid. And now, because this will be forming Grignard reagent, remember, don't confuse this and this. This will be C6H5MgBr. C6H5MgBr with CO2 Grignard reagent gives the acid. And now this acid further on reaction or by form with PBr3 gives us the acid halide, that is COBr, our target molecule. Now we are doing the other disconnection, that is our 1,2 disconnection CC. 1,2 disconnection, as we mentioned earlier in that brief summary which I had written on the first page, that implies the carbon atom, 2 carbon atoms away from this. So this is the functional group OH. So 1, 2, 2 carbons away. So we disconnect. Again we will get what? A Grignard reagent, and the other will be an epoxide ring. So this is the epoxide ring, this is the Grignard reagent, and when this is made to react, now this epoxide of course is formed from what? Alkene. That's why this can be written in this form, because this with per acids will give us rise to the epoxide ring. And the epoxide rings are very reactive. So this is the synthesis. This is the alkene with perbenzoic acid forming the epoxide ring, with which these react with Grignard reagent to finally give us the target molecule after epoxide ring opening. So O here with H, and the other end this will open up, so this other end will be connected to then the pH. That is our phenyl ring, and we get our target molecule. Now let's see the synthesis of carbonyl compounds similarly by these sort of disconnections. Now we are talking about 1,2. So this is our carbonyl compound. Carbonyl compound disconnected. This is 1, this is 2. So 2 carbons away, carbon 1, carbon 2. So again we will be getting what? R negative. But now this carbonyl, if we disconnect it here, if you recollect earlier, we won't be able to synthesize. So what is done? First of all, an FGI, as we had mentioned earlier in the first sheet where I described all these disconnections. So now when this on FGI, this will give us an alcohol. Now on disconnection, R negative and the epoxide ring, giving rise to finally the product. So for this carbonyl, a functional group interconversion to an OH, and then a 1,2 Cc disconnection. 1,2 Cc means an epoxide ring and a Grignard reagent. So this was the retrosynthesis, and now this is the synthesis. As we know, we will get our target molecule. On return, this will be oxidized, so we will get our carbonyl. Now let's see to this interesting reaction I have written. This reaction here implying that what if we try to disconnect it this way? Earlier on we had done it in a different way. Now when we try to disconnect it this way, what will we be getting? Again, for this carbonyl, when it is disconnected, this is the carbonyl 1, 2, R negative, R positive, and that is the other type, that is we are getting our enolate. So how do we get an enolate? By using this active methylene compound. So in order to get a carbon negative here, that means this time it is not disconnected here as a negative. This is disconnected as a positive. Again 1, 2, remember. If it is disconnected as a positive, then this will be negative. How can we get a negative over here? Because we know the alpha position here is acidic carbon. So in other words, we are talking about a carbene ion. Carbene ion generation means an active methylene compound, or this type enolate. So we write COC2H5, another electronegative group, so as to generate carbon negative over here. And now, how do we synthesize? Simply, in the presence of a base, this will give us the carbene ion. This carbene ion, which is highly stabilized because it has got this electron pulling withdrawing group and two of these 1,3-dicarbonyls, like it is for the active methylene compounds. This will react with RBr and we will get finally on hydrolysis our product, that is our carbonyl compound or this ketone. This 1,3-Cc disconnection. The last of these, as we know, the 1,3 disconnection means Cc, that we are disconnecting. This is the functional group, carbon number 1, carbon number 2, carbon number 3. So let's see to the disconnection. 1, 2, 3 disconnect. So R negative, this positive, and we get an alpha beta unsaturated. Always for 1,3-Cc, whether it is 1,3-Cc or 1,3-Rx, the synthetic equivalent is an alpha beta unsaturated carbonyl compound, and the other is this. Now R negative will be our Grignard reagent. The synthesis again, as we can see, R negative with alpha beta unsaturated, and we get this product. Now this example why I've written here is it is very interesting. It is very interesting. As you can see, it employs a little of our stereochemistry. Now see this interesting molecule where this is a diol, 6-membered ring with unsaturation at this end. Now this group CH2 attached as this end. So now as you can see, this and this, the 1 and the 4, they are cis, and this 1 and this 2, that is the vinylic group, they are trans. What does it imply? If you recollect your stereochemistry, that means this is now this bulky group CH2OH. This will occupy the equatorial, the more stable equatorial position. And if this is trans to it, we know that 1,2 di-equatorial is trans. Hence, this will also be at the equatorial position. And since this and this 1,4 are also cis, and we know 1,4 di-equatorial is trans, but 1,4 this axial equatorial is therefore what? Cis. 1,4, this will be therefore axial, this is equatorial, remember. Now see, if we how can we obtain this alcohol CH2OH? We very well know from lithium aluminum hydride. If an ester is reduced, it will give us this. So we write this, the FGI, so COET, that is our ester, which on coming back will lead to the formation of only this type of an alcohol. That is, on the 6-membered ring, we will get this alcohol as the equatorial, because the lithium aluminum hydride that will attack it from the less hindered side. Now what is the less hindered side? Because now this is equatorial, the less hindered side is the axial, because this is equatorial and this too is equatorial, this heavy group this side. So this will attack from which side? So therefore this will deliver the H positive from the other side, that is the axial side, and the alcohol ultimately will be formed from the carbonyl. This OH will be formed on this side. In other words, we are doing what? Kinetic control. Why kinetic? Because the hydride is attacking this carbonyl from the less hindered site. Which is the less hindered site? Since this and this are equatorial, the less hindered site is the axial, from where H negative is being deposited on this carbonyl. So H negative from that side. So obviously from the axial side. So formation of alcohol from the on the equatorial, that is our more stable alcohol is formed. Now to disconnect it further, remove this group, vinylic group, and when we remove this, we know this is 1,2,3 Cc disconnection, which will lead to again an alpha beta unsaturated carbonyl compound. So we get this alpha beta unsaturated carbonyl compound. Now let's see, because only the stereochemical aspects are important in this, otherwise it is just one and the same. So we are starting with this ester substituted. This is at this methyl group at this position. Now this on the formation. Now let's see, because the first step becomes the last step, so we will do reduction last. So this on reacting with this Grignard reagent, vinylic, what will it give us? The Grignard reagent obviously will attack to give us the trans 1,3, because this is 1,3, double bond shifts up, so the unsaturation therefore will lead to this formation of carbon positive here. So the carbon positive will be attacked by this R negative. And this R negative naturally will attack from which side, as we know, because this is on this side. So it will attack trans to this. So we will trans to this means that if this is equatorial, then this is also equatorial. Trans. This is a bulky group. So trans to this. So we will get our trans product. So see, there is a high level of stereoselectivity as well, because it can't attack from the same side, this bulky Grignard reagent. Therefore, because this group is present here at the, so it can't attack cis, it has to attack trans. So this is a six-membered ring. Remember, if this is equatorial, so the other portion from where this will be deposited will also be equatorial, so as to make it trans. 1,2-diequatorial is trans. So highly stereoselective, and we get this trans product. And now the last step, that is the reduction, and the reduction itself is under kinetic control, as I explained earlier, giving rise to this alcohol, and this carbonyl will be reduced because at the same time this will be reduced. This will be forming a CH2OH. We know very well why, and moreover this will be equatorial because this has occupied the equatorial position, so this is no complication over here. But here carbonyl, which is having two sides, again the carbon positive will be attacked in such a way so that we get our what alcohol this time? The axial alcohol. And what does it indicate at this end? That the attack will be in such a way so that the hydride ion, it attacks from which position? The other position, to give us this type of an alcohol, once again under kinetic control, because this alcohol will be the axial alcohol. The axial alcohol, implying that this axial here, the alcohol, because this will be cis to this, remember, axial equatorial. And it will be trans to the other. Trans to which one? Trans to this one, because this is equatorial and this is axial. We know 1,3-diaxial is cis. So one is equatorial, one is axial. This is equatorial, this is axial. I've shown it here to simplify things in this way. So see, this is CH2OH. That is our diol. I've shown the initial, that is our target molecule that has been formed here. It's so as to clear the stereochemistry. So this is equatorial because this is a bulky group, CH2OH, equatorial, and this is formed how? This is formed by reduction of our ester, the equatorial alcohol. This is equatorial, but and as this is trans, this too will be equatorial, this vinylic group, because 1,2-diequatorial is trans. Now, since this is equatorial and this, that is this end, is trans to it, so obviously this will be axial, because 1,3-diaxial is cis, and but 1,3-axial equatorial is trans. And we have managed it how? The stereoselectivity has been managed by kinetic control of the reduction, this reduction process, and this has been of course formed highly favored stereoselective because of the bulkiness of these two groups. So this did not attack cis, but it attacked trans, this Grignard reagent. That means trans attack means attack at the equatorial, because 1,2 di-equatorial is trans. So that is all for today. You can recollect the easy examples from this if you fail to follow, but I have if you're finding these ones a little more complicated, but that is just to make you aware as to how the disconnections can take place, so that you know the steps to take if you are asked to synthesize such a target molecule, which will be, first of all, this OH can be synthesized how, and this OH how? Simply by reduction. Reduction using the Grignard, using our lithium aluminium hydride, and that too under kinetic control. That means kinetic control simply implies that if heavy groups are present on one side, then the attack takes place from the other, or the other type of alcohol is formed. And in this case, as we know, which will be the alcohol, because this is also present in the equatorial position. So the deposition of H will take place such that both these are not on the same side. OH and this group are not, you know, this is equatorial, this is equatorial, this is therefore cis, because diaxial is cis. So by analogy, diequatorial is also cis. So this alcohol is formed OH in such a way so that these two do not come close to each other. This and this group does not come close to each other, which would have been the case had an equatorial alcohol been formed. Hence, this axial alcohol is formed. Moreover, remember that this is entirely controlled by the stereochemistry of this six-membered ring, where 1,2 trans means both these are di-equatorial. Similarly, 1,4 cis means 1,2,3,4 means that if this is equatorial, that implies the other OH will be therefore axial. Although axial is not the energetically favored, but as I've been stressing right from the beginning, that this reaction is under kinetic control, not under thermodynamic control. Had it been under thermodynamic control, then an equatorial alcohol would have been formed. But in this case, an axial one is formed, so that because the attack of this lithium aluminium hydride is from the less hindered site, and therefore this alcohol is formed. So good day to all of you.